Alright, so we're going to do 10.3 today. Come on, what are we doing here? 10.3 today, which is apply properties of chords. Chords were the line segments that are inside of the circle. We're going to apply properties of chords. Really short. We're already on slide 3 and there's only 7. Right? There's only a couple theorems here. They're very straightforward, they're very simple, they're very easy. It's hard for me to really jazz them up and make them challenging, but sometimes they do show up on the standardized tests. Properties of chords. So yep, nailed it. Two minor arcs are congruent, or the same size, if their corresponding chords are congruent. So what that means by corresponding chords, the arcs have endpoints, right? So the minor arcs have endpoints. So if I look at arc BA, the corresponding chord to it would be BA. Does this make sense? They share the same endpoints. One is an arc, but the other is a chord. And the corresponding arc for CD would be CD. Okay? So if we're talking about corresponding, the arc has endpoints BA, the chord has endpoints BA. That's how they match up. Right? If the chords are the same, so if BC, the chord, sorry, not BC. Let me do this in blue, actually. If BA, the chord, is congruent to CD, the chord, then we know that the arcs BA will be congruent to the arc CD. Remember, that's the symbol for arc. All right? So all it says is if the chords are the same, the arcs would have to be the same. Right? And vice versa. So if I give you the arcs are congruent, then the chords must be congruent. Okay? Notice that this only works for minor arcs. Does not work for major arcs. Only works for minor arcs. Okay? It gets confusing. All right? So the next thing says find the measure of arc BC. You'll notice I cannot do the little arc on PowerPoint, so I apologize for that. But arc BC, if the circles are congruent, so notice the circles have to be the same size, otherwise this won't work anymore. What do you mean does it matter? So here, right here? No, but I would rather have it written like that instead of written out, but I just can't do it. So find the measure of arc BC. So we want to find the measure of this. Well, we know that EF is congruent to BC, right? Everybody see that? Yeah. This is the radius. These are saying that the radii are the same. If the radii are the same, are the circles going to be the same size? Yeah. So if they're the same size circle, and both the chords are the same, how much does BC have to be? 125. 125. BC is congruent to EF, so therefore the arc EF must be congruent to the arc BC. Okay? The other property we have, nope. The other property, if one chord is a perpendicular bisector. One chord is a perpendicular bisector of another chord. Then the first chord is the diameter. Alright, so this one's a little wordy. If one chord is a perpendicular bisector of another chord, then the first chord is a diameter. Perpendicular means forms a right angle. Bisect means cut in half. So if you look at our shape here, it tells you that those are equal. So do you see how SQ bisects it? It cuts it in half.
Yeah.
It's also perpendicular to it. So our conclusion is that SQ must be a diameter. SQ must be a diameter. And the opposite to that, a little different, but same idea. If a diameter, the diameter EG, see how it goes to the center this time? They give you the center. If a diameter EG is perpendicular to a chord, that chord is FD, then the diameter bisects the chord and its arc. So that means it bisects the chord, so it cuts into what? Two equal pieces. So FH must be congruent to HD. Does that make sense? And it says it bisects its arc. So what would the arc be? What would the arc be? FG, the arc, must be congruent to GD, the other arc. Okay? So a diameter, if it's perpendicular, it must cut it into two equal pieces. Alright? So this means that FH will be congruent to HD, and arc FH will be congruent to, sorry, not FH, FG will be congruent to arc GD. Okay.
So is it the same thing backwards?
Thank you for raising your hand. It's very similar. It's very similar. It's slightly different, though. Yes, ma'am? What's up?
Well, like you say, if the diameter is perpendicular to the chord, but if the chord is perpendicular, it's perpendicular to another chord. So, it's kind of like
Yeah, it just gets a little wordy. I didn't want to say vice versa because it's going to be a little confusing. That's why I wrote this one out. The other one I didn't. Yes, they're incredibly related. Can we go on?
Yeah.
Last one. Find the length of BD. Not the last one. Well, what is AC first?
Diameter.
And is it perpendicular to the chord?
Yes.
So what do we know? It cuts the chord into two equal parts. So BD has to be 12. Remember, BD is the whole thing. So first we would do BF equals 6, and then we know that the whole thing has to equal 12. Yes, ma'am? In that case, yes, because the other piece has to be equal. So it's 6. 6 plus 6, 12. Or double it. Depends on what I give you. If I give you a situation like this, yes, you would always double it. Arden? Which arc? You need to do a little bit. Which one? BCD? We wouldn't know unless they give it to us. 180 is for a diameter, a semicircle. This is not a semicircle because it doesn't go through the center. Correct. We don't know what it is unless they give us some more information. Yes, sir.
Right on when, like, if there's a difference in when, like, one of the angles are right angle, and the other one's not right angle.
Correct. So this would be a right angle. So you want to say that CD would be 90.
Yeah.
However, remember our definition of arc was based off the central angle. So it has to be the angle at the center. This angle is not at the center. Good question, though. Okay. Is that cleared up? Okay. Last problem of the day. Last slide of the day. Two chords are congruent or the same size if they are equidistant from the center. We measure equidistant in a straight line. So if you walk in a straight line, you form a perpendicular, and those two must be congruent. So see how FE and EG are the same length, the same distance from the center? if they are the same distance from the center, then the chords must be congruent. So here, AB would be congruent to CD.
Is that the color straight line?
Which one? FEG?
Yeah.
No.
What are the boxes?
What does the boxes mean?
Right.
Right angles. Because if you ever draw a line, if you're trying to find the shortest way to a line, you want to form a perpendicular with it, which is why there's the right angle there. Okay. The obtuse angle? No, it's just, it hits E and makes an angle and it goes straight again. So it's not a curve, like a circle, but it's two straight lines that come together at E. But they are not straight. Like it's not straight overall. There's a bend, a turn. Last one. In the diagram, AB equals CD. Oh, and vice versa. For this one, sorry. Vice versa. These are really weird. I realize that they're a little challenging when you do the homework, though. They just ask you to, all they do is they give you a shape, and it's very obvious what you need to put together. In the diagram, AB equals CD, and they both equal 12, find EF. Well, if the chords are both equal, then we know that they're the same distance from the center. Does that make sense? So we know that these must be congruent. So we know that 3x equals 7x minus 8. We subtract 7x. So we get negative 4x equals negative 8. So x equals 2. Is that what I asked for? No, I asked for EF. So I have to plug it back in. EF is 2 times 3. So EF equals 6. EF equals 6. Okay. I have an announcement to make, so I'm going to show you your homework. Please write it down. It's very short. Alright. Very short. Your homework is very short. I know. Hang on. I know it's 2, so I plug in EF. 3 times 2 is 6. Your homework, please. Your homework is 1, 2, 3. It's very short. I mean, it's like 1, 2, 3, 4, 5, 6. Oh, why did it stop? There's your homework. Okay. It's very short. It should be very easy. Okay? Write it down, please. Stop watching the guys. Write it down, please. Ten seconds. Write it down quick. 10 seconds. Sorry.